Okay, the next speaker in the afternoon is André Oliveira, that he will speak on Lagrangian of Hecke cycles.
Thank you. So thank you for the invitation. It's a great pleasure to be here celebrating Oscar's contribution and birthday. So following Anna's approach, I'm not a child of Oscar. I'm more like a nephew, right? Yeah. So I met Oscar while I was a PhD student. I was visiting Madrid, back in this beautiful building at CITIC, right? In the residency. And since then we've been collaborating regularly, and it's pretty great. So thank you, Oscar. So today I'm not going to talk about actually a topic I usually work with Oscar. That's more like in the spirit of Peter's talk. So I'm going to talk about joint work in progress with Emilio Franco, Robbie Hansen, Johannes Horn, and also some parts of the talk with Emilio, Peter Gotten, and Anna Fiore. Okay, so okay, let's start with the basic object. The object, the notation, and so on. So most of you know already what this stuff. So X will be a fixed curve, smooth, projective, C with the genus of options. G is 2 with canonical bundle vector. And by M, I'll mean MI0. So this is the moduli space of Higgs bundles, which you already know that they are pairs consisting of a vector bundle and a twisted holomorphic anamorphism of B. K of rank R and degree 0. So we always in degree 0. So the rank is the rank of B. Okay, so now if I consider N to be the moduli of vector bundles on X, everything is on X, of the same rank and degree. Then, so here I'm not talking about semi-stability, but in semi-stable Higgs bundles for this is just one for which every invariant subbundle, or invariant bundle, this map has degree less or equal than 0. So here I don't test every subbundle, but here for the vector bundles I test all of them. So I can have semi-stable Higgs bundles with underlying bundle not semi-stable. And the ones for which the underlying bundle are semi-stable are part of the Higgs bundle moduli space and give an inclusion of the cotangent bundle of N to N into N. And this is open and X. Semi-stability is an open condition. Okay, so so this is a quasi-projective variety. This is N is projective, but it may be singular precisely at the strictly semi-stable points. So by omega, I'll mean a holomorphic symplectic form on M, which extends the canonical one here. So I'll be talking about, whenever I talk about Lagrangians, this is the symplectic form I'll be considering. So for instance, N is Lagrangian in name. All right, so Okay.
Considering stable parts or
Right. I should say that this is everything about on the smooth focus. Good. Okay, so now let me go to the kitchen map that Anna already mentioned. So this is the map. I'm going to be slightly, I needed to say some more details about it. So this, as Anna said, this out of a Higgs bundle or a point represented by a Higgs bundle gives me the coefficients of the characteristic polynomial of the Higgs field, which, since this is a K-twisted endomorphism, these are actually live in sections, polymorphic sections of powers of K. And we have a whole bunch of them, ranks from 1 to R, from the trace until the determinant. And it's easy to see that this is actually the dimension of E is half the dimension of M, which is even. All right, so now out of an element here, I want to see what's the fiber of this map, of the Hitchin map from an element there. So out of an element here, we can construct what's so-called a spectral curve associated to A. And this is a curve inside the total space of K in its surface, which then maps to X. And somehow, so I'm not going to give details on this, but this is a curve which somehow records the eigenvalues of the Higgs field. Okay, so I have a map here. This map, let me call it the same, using the same letter here. And from a point here, this map is an R cover, ramified. Ramified R cover. And you can think of it as over a point in X, it gives you the R eigenvalues of the Higgs field, which can have multiplicities, and that's where the ramification occurs. So all these curves lie in the same linear system, and the linear system is actually on the pullback of the canonical bundle to its total space. And then it follows from that for generic points in the base, these spectral curves are smooth. Okay, so a generic smooth. Okay. Right, so now the fiber of this Hitchin map, so this is a proper subjective map, and the fiber, the construction of this fiber, or the description, follows from works of many people: Nigel, Carlos Simpson, Beauville, Narasimhan Ramanan, and maybe I should say also Shaw. And this is the Jacobian of XA, but now compactified. So this is the compactified Jacobian of XA. So this is the moduli of torsion. We put it like this. Rank 1. Torsion 3 shifts on XA of degree delta, and this delta is R minus 1, G minus 1. So if the curve is smooth, so numerically this is really the Jacobian of line bundles of this degree. If not, then the Jacobian is not compact. So here we have the generalized Jacobian of XA inside this as an open dense space. If it's not, then you have to add this rank 1 torsion free sheaves. And here the correspondence is that for such an object over a curve, you build a bundle which is given by this. You just push forward the sheaf to the base curve, and the Higgs field is induced by this map. So this lambda, what's this lambda? So this lambda is a topological section. So if you pull back the canonical bundle to its total space, then you have a topological section, one of P equals P, right? And it restricts, taking the restriction to the spectral curve, and then multiplication by this section induces a Higgs field. Okay, so this is it's called the spectral data of the Higgs bundle. So giving you a Higgs bundle or the spectral data is the same, gives you the same information. Okay, so one important thing is that this map is then an integral system, a complete integral system actually, and then it's Lagrangian. So the fiber is Lagrangian. Okay. So take now the discriminant locus. So the set of points here for which the spectral curve is singular, right? And we're interested in Lagrangians mapping to this discriminant locus. So there is a lot of interest in Lagrangians of M for various reasons. One of them is mirror symmetry. I'll try to say some words about that in the end. But we are interested in those which map, or which they map to the singular locus, so are all contained in the singular spectral curves. Okay, so now let's construct our Lagrangians. Which do map to the discriminant locus. Okay, so construction. Right, so now take K, a positive integer. I'm going to allow to be 0 also, even though that's going to be a degenerate case. And so let's take BK, subspace of this hitching base, such that it gives points such that the corresponding spectral curve is integral. So reduced and irreducible, has K nodes, K ordinary double points, and no other singularity. Right? So B0 is really the state of smooth spectral curves, and this is then. So the discriminant locus has a positive codimension. And you know, BK plus 1 is contained in the closure of BK, because you can generate a nodal curve to acquire one more node. So now let's fix one point here in one of these BKs, and take NA with a set of nodes, let's say, dA be the norm of NA. So this is a divisor, an effective divisor of degree K on the curve, right? And take WA, define this as the branch divisor of this covering. And it turns out that WA is actually of the form 2dA plus XA, where so this part of this divisor, this branch divisor, records the singularities of the spectral curve. It is because we're taking notes, and that A is the smooth ramification. So it turns out that the line bundle associated to this divisor is always K to the R times R minus 1, and this implies that our number of nodes is bounded by this number. Okay, so we have this maximal number of nodes in this. Okay. Which is when I say equals.
Can I just ask a question? Is this statement completely obvious that K plus 1 is certainly it's in the closure of the union of the rest, but is it really clear that it's built up?
If you have a nodal curve with K nodes exactly, and you deform it to acquire.
Yeah, these are spectral curves.
Yeah, right.
I mean, you can't do it.
Right. No, yeah, you have to do the deformations inside the linear system. Yeah, but you can do it.
You can do it.
Yeah, you can look at the equations and so on. Okay. Right now. Okay, so right. Okay, so now let's take. So I'm constructing the Lagrangians. Okay, take the normalization map. So XA tilde is going to be a smooth curve, and we have this diagram. I tilde, and out of this map, we have this. If you take the generalized Jacobian of your spectral curve and take the pullback to the Jacobian of the smooth normalization, then this is actually a C star to the K bundle, which is why this is called a semi-abelian variety. This does not extend to the compactification, so it's only on the generalized Jacobian. And now we move A in decay. And now let's consider the following. So consider J delta to be the relative generalized Jacobian of spectral curves over dk. Okay. And I'm really taking generalized Jacobian right, over each one. And here the relative Jacobian of normalizations, of the corresponding normalizations. Here is this. And still over dk. And now let's choose a section of this relative Jacobian, and one of them can be, for instance, sigma of A, section sigma. Okay, R minus 1 over 2. So probably, yeah, I should have fixed an A, right? And so we have a section. Any other length of the appropriate degree would work. And now, so now this map here, N star, induces a corresponding map on the relative generalized Jacobians and Jacobian. And now define, with all this data, define the following. So take the image of this section, right? So, right? And take the inverse image of the section under this map. So this family of generalized Jacobians is inside the moduli space. That's the spectral correspondence. And now close it. Okay. So here in this closure, I'm taking the closure here and on the base. Okay. Right. So for instance, so what's the intersection of this space with a Hitchin fiber where A is for A in BK? This is just the closure of the inverse image of that map, so of the pullback map. Right, so we have sigma A, which here, I'm taking its fiber and I'm now closing it. And this is like a product of P1s. Okay, it's a closure of that, of this. Okay. All right, so the theorem is that theorems myself is that these guys are Lagrangian. In there. And the idea is actually very, very simple. So take P in this space, generic. And by generic, I mean that P is really in the generalized Jacobian of some spectral curve in BK. So it's, I'm not closing it, I'm not going to the boundary of this generalized Jacobian. It's really a line bundle for A there, and it's BK. And okay, so now take the tangent space to our space. This lives inside the tangent space, the Higgs bundle moduli space at the same point. And now I'm going to take the differential of the Hitchin maps and take the tangent space to the Hitchin base at the corresponding point. It's a vector space that's the same as before, as the Hitchin base. So at some points, the Hitchin map drops the rank, but these are not in those points. Hitchin proved that those, so the fact that this is subjective was proved by Nigel for rank 2, and then more recently, actually not yet published, but Johannes Horn and Schulzen Na proved that this for higher rank. So since I'm not going to the boundary of this generalized Jacobian, I'm safe. The Hitchin map is the differential of the Hitchin map is subjective. So here inside, I have the tangent space to the fiber at this point. Okay, so this is minus I. So 0 to R minus 1. So this is tangent space. Okay. And here I want the tangent space at the point P over not the entire generalized Jacobian, but only of this fiber. So, and this is then star minus 1 of sigma of A. And this is, turns out that this is isomorphic to H0 of this skyscraper shift over the divisor which measures the singularities. I have this here an inclusion, and here I have a map which is H1 by tilde or star XA, and this is the tangent space to sigma of A of the Jacobian of the normalized spectrum. So here on this side, I'm basically taking the differential of this sequence, nothing else. Okay. So here I have conclusion. And on this side, so the spectral curve parameterizes deformations, sorry, the Hitchin-based parameterizes deformations of the spectral curve within the total space of K and within the same linear system. So here we want a tangent space is dk, and these correspond to equisingular deformations which preserve the singularities. And so here we have the Italian school that helped us, and then there's a specific, very explicit way of parameterizing those, which in this case turns out to be H0 of the put for of the structure sheaf of the normalization listed by K. So these are really the equisingular deformations of the spectral curve inside the same linear system, which you can think of it as a tangent space to this multi-VK. And then this actually turns out to be, there's a long exact sequence, and it's here. So, so the symplectic form, so the Hitchin base is Lagrangian, and the symplectic form here pairs these two. And these two sequences, if you look at them, they are. So here I'm taking this subspace of the Hitchin fiber, and here I'm taking the annihilator. And so the symplectic form here is really 0. And moreover, the dimension of this guy is the sum of these two, but this is isomorphic to that one. So it's the dimension of the base, which is half dimension. And so that's why it's Lagrangian. Okay. Okay. So now
Yeah.
Right. So okay. So let me just give you a property of these Lagrangians. Is that if Vp is a Higgs bundle representing a point in one of these Lagrangians, then and which is in a fiber over some generic point of pk, then it's easy to see that Vp is a Hecke modification of the Higgs bundle given by this. Along TBA. Right, so any Higgs bundle there can be written as a Hecke modification of this Higgs bundle. So remember, this is a line bundle on the normalization. We push it down, we get a vector bundle, and the Higgs field is obtained in a similar way, like in the spectral correspondence. So that's why we call them Lagrangians of Hecke cycles. And the cycles are exactly the P1s here. These P1s parameterize Hecke modifications over each node. Right? Okay. Now let's go to one extreme and very degenerate case, so the minimal case. K equals 0. For K equals 0, this is very degenerate. So remember then the spectral curve is smooth, so these curves are equal. So there's basically nothing. And so in this case, actually L sigma 0 is the Hitching set. So somehow these Lagrangians generalize somehow the Hitching section. Okay. So the other extreme case, it's a maximal case. And here, so remember that then K is, and let me just, to simplify, let me consider R equals 2. So 2G minus 2. And in this, everything that has to do with this maximal case is the work with Emilio Franco, Peter Gotten, and then Theo. All right. So in this case, what happens? All right, just. Okay. So in this case, remember that our branch divisor was this 2dA plus smooth ramification. But then in here, there's no space for smooth ramification. This implies that ODA squared is K squared. So ODA KL for some L for some line bundle, two torsion line bundle, such that L is not trivial, because I want the spectral curves to be reduced. Okay. All right. So now this means that I can write. So this imposes more constraints on these dividers. So I can write my maximal case Lagrangian as the union of these Lagrangians. So these are irreducible components of these Lagrangians, for which here I'm fixing one of these 2 to the 2g minus 1 roots of the. So I have 5 minutes. Okay, I'm gonna do. Okay, so now let's fix one such L, and let's consider here ML to be the space of Higgs bundles which are fixed when we tensor them by this two torsion line bundle, right? So this is a locus inside our moduli space. And it turns out that this ML is hyperkähler, submanifold. Hyperkähler submanifolds are supposed to be or hyperholomorphic are supposed to be supporting DDB branes. So the DDB branes are hyperholomorphic separated with a hyperholomorphic bundle. I'm going to deal or consider only the supports. And our Lagrangian, yeah.
Could you write from the pair in hyperkähler on to the right? Like the ML, we can see the ML with the camera. Also from the pair.
Is there some problem with the camera?
It's because like there's like two planes and like none of them is compatible with the.
What do you want me to do?
So maybe like ML and high should be erased, and from pair onwards that's visible.
You can write the line.
Okay.
Draw a line, draw a line, draw a line.
Yeah, maybe I can draw a line.
Yeah. Okay. So I erased it. Was it like this?
Yeah, okay, yeah.
Okay. ML hyperkähler. Okay. So then it's, we think of this as supporting a DDB brane. And this is Lagrangian, complex Lagrangian. So complex Lagrangian are supposed to support EAA branes. So we start flat bundles, let's be simple, EAA brane. So these objects are supposed to be interchanged under mirror symmetry. And the theorem that we proved, that go with Emilio, Peter, and André, is that indeed ML and support dual branes. So, okay, so we actually this is already published in 21. So we consider this. Actually, so we consider these Lagrangians before the ones I was explaining there. The proof that they are Lagrangians is different. And our theorem is actually much stronger than this. We consider actually the sheaves on these subvarieties and so on, and not just in rank 2, in higher rank. But now we are somehow.
What does it mean that they are dual branes?
They are exchanged under mirror symmetry, which means for the purpose of mathematicians, let's say, or whatever, that their spectral data is exchanged, and the spectral data of the sheaves corresponding here is exchanged under Fourier-Mukai transform. Right? So we did it really explicitly gave you the Fourier-Mukai transforms. Okay, so how much?
No, you have 10 minutes.
How much?
Yeah, it was a mistake.
Oh, it was a mistake. Next time now. Okay. So when I ask you 5 minutes, I'm saying that I have 20 minutes. Okay. All right. So right. So now, so this we've done before. Now what we are trying to study more about these supports of these varieties, especially these ones. Actually, we are trying to understand what's going on when they intersect the new photon. And what we've found so far, I can tell you one thing is that, again, is that, so first of all, yeah, let me set V a Higgs bundle representing a point in this variety, in this Lagrangian, and for A maximal, right? Then first of all, so one can see that these Lagrangians are actually C-star invariants. So the C-star action scaling the Higgs field preserves both these two, and we proved that this is only in rank 2. Then the limits, when we take the limits, 0, right, is either so this tip of the nilpotent cone right? It's actually this is an SL2C version of this Lagrangian. It's either this one, which in the since it's the highest possible degree in the nilpotent cone in the language that Anna was telling us is a very stable fixed bundle. There's nothing in the nilpotent cone flowing to there, or it's a wobbly fixed bundle. So these are the only possible very stable Higgs bundle which arises from the guys here is this one, right? This is in rank 2. So this says that this space is somehow like the complement of the one which I wouldn't say, I don't know complement, but it's well maybe of the one considered by Nigel and Thomas, where they considered flows of Higgs bundles whose limit is a very stable Higgs bundle. So these are really wobbly. Okay, so they're these guys, except for this one, it's always a limit of a C star flow inside the nilpotent cone. Right? And we proved it exactly using the criterion that Nigel and Thomas had in their paper, which exactly characterizes wobbly Higgs bundles. And this is important here that we have in rank 2.
Yeah, at some point you got to rank 2. I mean, some
also. Yeah, I got in rank 2 what the maximal case. Right, but all of this up until here, I just was going on for simplicity. Here it's not needed, rank 2. Here it's needed. Okay. All right, so now just to finish, going back now to the general case. And general case means that K is not maximal anymore. Now, so this, I can write these fixed points. This makes sense in for any rank, right? These definitions for any rank. Yeah, actually, let me, yeah, sorry. Let me keep it in rank 2. Yeah, let me keep it in rank 2. So I can write the union. I can consider the union of all these fixed point loci, right? And this turns out, let me write it like this, as C to G minus 2. So this C to G minus 2 is is again a maximal case of this loci, CK, which is called a critical case, critical loci, which were considered by Nigel 2019. This is the loci of the Higgs bundle moduli where the Hitchin map drops rank, right? And the drop of the rank is measured by this K. Okay, and well, again, this actually maps to VK, probably both. And the maximal one, rank 2, is exactly this union. And now I'm going to end with a question because of the following. So these two are dual branes, and this is a maximal case. So it's natural to conjecture that if here we consider our Lagrangians not in the maximal case, may be dual in this sense, so that they support dual branes to this CK. So there are evidences that L sigma K and CK should, I'm going to put this in quote, support dual brands. This is Lagrangian, support the PAA, okay? And the evidences are not only thinking about the maximum phase, but really thinking on the spectral data on the Fourier-Mukai transform. So the spectral data of this one is similar, very similar to the one of this one. Okay. However, and this is a big however. So each improve that T1 K equals 1 is not hyperkernel. So they cannot be. So this does not support the BBB brain. So the question is what's going on here? Probably these evidences are not true, or if they are, we don't know what's going on, because there's this conjecture that BAA should be transformed and the Fourier-Mukai transform into a BBB, which is supported on a hyperkähler submanifold. If that's the case, then I mean, we have to keep in mind that this is, let's say, mirror symmetry over with singular spectral curves. Much less is known in that case. But, well, I don't want to say much because maybe these evidence are just that and not the true story. Because that says that it cannot be. CK is not, C1 is not a BBB brain. Okay? So, I'll stop here.
Thank you. Are there any questions or comments?
So if I understand correctly, I mean, in many situations, we do have the supports, they're hyperkähler or they're Lagrangian, and you're missing the Fourier-Mukai transform. Here, you're saying the opposite, right? You have the Fourier-Mukai transform, more or less, but you are missing the property of the hyperkähler. Is that what you?
It's not hyperkähler for C1.
But do you have a Fourier-Mukai?
That's where we still don't have.
Ah,
We kind of are heading to that, and there are some evidences, like strong evidence, that the Fourier-Mukai in this case behaves like in this case, which works. And the spectral data in this case is very similar to the one here. And so this, and moreover, I mean, there's also this other very degenerate case. This is the maximal one. Remember that the minimal one was K equals 0. That was a Hitchin section. And you can, I mean, you can define here the 0 critical loci. And the closure of that is the entire moduli space. And the dual of the Hitchin section is the entire level of supports, just the complete moduli space. So, yeah, I don't know. But we don't have that really. Yeah. Maybe that's.
And that is for any genus, no? For genus equal to 2, do you have something special? Or?
Here we didn't try for genus equals 2. We actually here in this case, but this is different. This is not to do with nursing. This is the description of the Lagrangians, how they intersect the real Poisson cone. We're trying to do it in genus 2. On the
Okay. Any other question or comment? Yeah.
I was just wondering if there are any other types of singularities for which this game would work. And you know, there are things like nodes at cusp where I don't think it would, but I was thinking if you think of the Higgs field over a point as being a matrix, then you get the multiplicity patterns of eigenvalues. And and take the sort of singularities that induce, sort of threefold node or threefold, etc., would you get a similar picture?
I think, well, if you go out of, I believe, so if you don't, you take on maybe A-type singularities, maybe that's, I think it does, but if you go out of A-type singularities, I don't know.
Yeah.
I have no idea. I mean, most of the construction of this, I would say that it, well, I don't know.
Well, for cusp, the generalized Jacobian just gains an extra
Yeah,
dimension.
it's the same thing.
And you lose 2 dimensions
Right, right.
on the constraints.
Uh-huh. Yeah,
It doesn't work.
yeah, never thought about it.
Any other question? If not, let's thank the speaker.